I'm David Fowler. This is Damian Edwards.
Hello.
And the goal, last year we had a talk on diagnosing ASP.NET Core issues, and we want to kind of take it up notch this year and dive deeper into different specific kinds of issues you may have scaling your ASP.NET Core applications. How many of you guys have experienced a scale issue before in production? No one? I don't believe you. OK, everyone.
Everyone,
right? Yeah.
surely.
Awesome. Well, I haven't. We don't build real applications. We work on the framework team. We mostly see people's applications that come through our support channels. So people running on Azure App Service or people running internally will send us emails going, oh, my app isn't responding. Why is that happening? And we'll have a dev go in and dive in for a couple of days to figure out.
It's actually probably fair to say that most apps that we do get the privilege to see are ones that are broken somehow.
Yeah.
Because they don't call us unless there's a problem.
And sometimes it's not always their fault. It could be the framework's fault. So we kind of have learned some things over the past few years, and we kind of want to share it with you guys.
Yes.
So we spend tons of time looking at customer issues. So what is scale? Scale is not performance per se. Scale, I describe it as a measure of user request connections per scale unit. A scale unit can be a machine, a container, something that has actual compute resources, right? So more scale means you can handle more of those units per your actual scale unit.
And so sometimes we have to trade off scale against performance of an individual thing as well. So.
Right. So quoting Scott Hansman, if you do nothing, you can scale it infinitely. Right? So do less, you can do more with less resources.
So it's always good to try and do as little as possible. That's my philosophy in life.
Yeah. There's two kinds of scaling horizontally or scaling outwards. That's where you add more resources. So if you have some VM of some size on somewhere, adding more of those is scaling out. Scaling up is where you increase the VM's capacity or scale unit's capacity. So adding more memory to a container, adding more CPU to a container, that's scaling up and scaling out. It's a pretty basic.
So you can, and this can apply to every style of app. You can scale out your database with things like sharding or going to something that's clustered.
Yeah.
And you can do vertical scale, obviously, but just having a bigger server.
Or you can use serverless, and then you just don't have to worry about it.
Serverless, you have to worry about. Someone else's
scale.
problem. And
just
then
pay money.
The poor person who has to manage that, who has to worry about scale.
So what is your app scale? There are kind of two main themes. The first is you did some work that didn't clean up stuff. So you have a resource leak, for example, a memory leak, or a file handle leak, or a socket leak. Or you're creating work faster than that work can be finished. So you could think of a thing where you're handling too many requests, and things are coming in, and they aren't finishing fast enough to actually use the CPU resources, right?
Yeah, and the second one there is a real reason why what we often see is my application worked just fine. Works on my machine, right? Works on my machine. Worked in production perfectly fine for 6 months. And then something changed. Like you got 5% more traffic than you did previously. Or some other part of the infrastructure started making a slightly different decision, which resulted in some impact on your application. And suddenly the exact same application that had been running perfectly well before doesn't just start getting slower or start having a little bit of trouble. It goes through a period of like, that's not right, and then it just falls on the floor.
Right.
Okay, and we're going to see in this talk some of the things that why you get this non-linear relationship between, well, it seems to be working really well, and now it doesn't work at all. And not this slow, gradual decline.
All right, so what affects scale? So this isn't intended to be a full list of things. They're mostly common things to look out for in your applications. So there's CPU, memory, and I/O. And I/O can be network or disk. So CPU, you have a hot path on your request path, some expensive algorithm like trying to find primes or trying to do, I don't know, image compression or something like that. Contended lock, so imagine you have some shared resource that all requests come in to get, and has a giant lock around that thing. There are memory leaks, so imagine you had some cache somewhere that wasn't bounded, as an example of a leak. Things that allocate more than they have to. So imagine you're trying to read a file from the network, and you read a giant string to memory, as an example of that scenario. Port exhaustion. So imagine you weren't disposing your HTTP clients properly. You could exhaust the ephemeral ports on the machine, which could lead to issues with the HTTP client calls. Not looking at your disk storage. Imagine you were actually burnt up the disk and they ran out of space. That's kind of an example.
Who's ever had a server fail because their disk filled up because of logs? Yeah.
Wow.
That happens a lot.
Is that common, huh?
Yep.
Blocking I/O is one that's dear to our hearts.
Yes, indeed.
If you've seen my tweets about async, blocking and async void, and async is terrible and great at the same time. Blocking is really bad. It causes the thread pool to be starved, and we'll see more of that later in this talk. Bandwidth and latency. You have a fixed amount of bandwidth in your network servers, and if you go over that, you can't serve enough requests.
Right. And sometimes these things end up being related. So a problem in one area will lead to a problem in the other. And so you might look at one of these things and go, well, I have all the bandwidth in the world, it's never going to be a problem. Or I have so many cores, it's never going to be an issue. And then you introduce a contended lock, and now suddenly that doesn't matter. Or you end up filling up your bandwidth, which causes increased latency, which now means your queues get full, which now means timeouts occur, which now is da-da-da-da-da-da.
Cascading failures.
Cascading failures, right? So people talk about cascading failures in the arena of things like distributed application design and services. But the reality is, even in the context of a single process running on one machine, it's a mini microcosm of a distributed application right there. Because you've got CPU, and you've got I/O, and you've got memory, and you've got shared resources. And any one problem in any of those areas can cause a problem in another, as we'll hopefully see.
Awesome. So that was machine-level resources, so CPU, memory, and I/O. For the CLR itself, there are a bunch of shared things. So the GC, is shared across the entire application. The thread pool is shared across the entire application. So when you cause issues in a thread pool or GC, it affects the entire application. So for example, if you experience thread pool starvation, your timers won't fire because the timer uses the thread pool as well. So you end up getting these cascading events where if one subsystem goes down, the entire app begins to fail horribly, right? Errors are very expensive. If you throw an exception, it has to walk the entire stack. That is a super expensive operation, so you don't want to throw exceptions very often. Locks that are very hot. We'll see a demo of that in the app as we go along. And sync I/O is kind of another thing that affects scale.
And sometimes these things aren't in your app.
Yep.
Sometimes these things are in the framework or in the core effects itself, and then people log bugs because we find places we didn't realize had a contended lock or was doing synchronous I/O, or et cetera, et cetera, et cetera. So,
yep.
And as David said, GC and thread pool are kind of intrinsics. You don't really get to control those. They're shared and they're in the platform. You can impact what they do, because typically they're only doing work because you did work in your application. But you kind of have to work within the bounds of what those things can do. You have to understand what they do in order to make sure you don't overuse them. So
there was a fun example of a service that went down. I can't say which one went down. Microsoft service that went down because of calls to string.intern. Intern is a lock inside the CLR, a single lock across the entire process. So guess what happened? Request came in, string intern happened, and it took the entire site down because it was blocking on that lock. It's a super hot lock. Async programming. Does anyone here use async await daily in their lives? Everyone?
Good. Most people.
Yeah, it's good. It's good to use it. If you use it incorrectly, it's really bad. So using it correctly can give you like massive skill improvements. Using it incorrectly can actually make it worse than it was before you changed to async in the first place.
Yeah.
.NET has a bunch of async traps, mostly because we came from a synchronous world, and we got to add async as a bolt-on. So APIs kind of have sync and async APIs, and they don't interact well together. So there's kind of a bunch of issues if you use certain things in certain orders. And you'll see a bunch of those traps as we go through the talk in general. The main rule is just don't block thread pool threads. That's
Ever.
kind of main, ever.
Just don't block, ever. And what do we mean by block? Can you elaborate?
Don't stop the thread from running, doing useful work. Don't call task.wait, task.result, task. You'll see a bunch of APIs that you shouldn't call.
Okay.
All right. Does anyone here do testing before going to production? Tell the truth. No, you don't. No, you don't.
No, of course not. Production is my testing.
So usually what we see, people run a load test on their local machine, their dev box. They run like A/B with 100 connections, and then that's good. Then they put it in production, and it falls over at some point, right? Mature teams, what I've seen them do is they run a bunch of scale tests, figure out the limits of each of their scale units, and then put in like hard limits that fail aggressively if you go over that limit. So for example, the Skype team, they run a scale test, and they'll find the max number of concurrent connections that they can handle for any machine, and they'll put a number in saying we can only handle 200 for this machine as they deploy. So you should have a fixed CPU and memory usage for any RPS. That's how you would go about testing.
Of a certain style of work,
yeah.
Right?
For your workload. One issue we see people ask us now, how about this blast scale? And we always go, you should try it yourself on your hardware in your environment to make sure that you understand for your specific scenario how your workflow.
So if that was your question at the end of this talk, you would come up and say, so David, that was a great talk. Can you tell me how my application will scale? The answer is always no. We can't. Like, you need to try it yourself. There are so many variables that will never, or how does SignalR scale? We used to get that one forever, right? Because it scales really well in our tests. I don't know what it's going to do in yours. You really need to learn how to do that testing yourself and some of the techniques you're going to learn today.
Yep. All right, so the cycle is you run a load test, find a bottleneck, and fix issues. And there are various tools you can use. You should look at the counters for every subsystem in .NET, so the number of GCs happening, the number of threads allocated, the CPU usage, the memory usage, and look at those things to figure out where your limits are for each scenario. And the normal thing you do is you run a load test, you hit some RPS, and you say, OK, that's OK. And you run a profile to see why you're hitting that RPS. If it's OK, then you leave it as that's your max, and you can scale it from there. So let's move on. All right, so CPU, the checklist for going through.
One more thing before we move on from load testing.
Yep.
I've always liked to differentiate between load testing and stress testing. And so load testing, I think, is what I would use this term to describe what David is saying, which is you're finding what works well within, someone says, we need to support X number of RPS for this system or transactions per second. And you do some load testing to figure out how many resources you'll need. Great, now you know that you can handle what you said you were going to do. Stress testing is figuring out what happens when you go over that. How is your system going to behave when you give it more load than what you designed it for or what you know it can handle? Because the failure modes are varied. Right? How your system will fail when you go beyond what you think your capacity is will vary massively depending on where your scale problem is. And stress testing is a great way to find that. And there are different types of loads and different types of stresses that you can apply to your system. It could be more work because you give it more requests. It could be constrained memory because you're in a noisy neighbors situation where there's more processes running on that same machine. It could be a failure of some kind where you're running in a containerized environment or in some type of cloud environment and you lose a node. And so now your lovely load balance farm of 20 machines goes down to 19. And if you were on the edge, guess what? The 19 now are going to have a lot more traffic than they did before, et cetera, et cetera, et cetera. So that's a little bit different to load testing, but it's super important to understand how the application will behave when you give it too much. All right? Do you want it to fall flat on the floor? Or do you, as David said, do you want to have a nice, maybe another part of the system that goes, oh, I'm getting close, let me just fail everything or send it out somewhere else when I get to that limit?
There's a funny story. I've seen people end up having autoscale turn on some Azure service, and it scaling up because of a bug in the user application, and they end up paying a ton of money because the bug kind of amplified the scale. It's like, oh, you can't handle this much load, so you need more load. So it added more scale and caused the issue to be worse, right? This kind of issue, it's an interesting thing to look at. All right, the checklist for scalability. So I made 3 categories here, like machine, CLR, and application logic. These aren't the full list, but it's kind of what we think are common enough that we've seen in applications. So looking at CPU usage in general to see where you're at. Thread pool, the number of work items and the number of worker threads that are currently allocated. Looking at the number of collections, Gen 0, Gen 1, Gen 2. Hot locked in the process for app logic. Usually JSON, handling JSON pillars from incoming or outgoing are hot pass for CPU or chatty I/O. Doing a lot of small writes to the network is really bad for CPU performance. For memory, looking at memory usage, looking at number of threads, because each thread is a megabyte of stack. Timers is kind of a big one that we'll talk about going forward. The GC heap size themselves, not collections, but the heap size. For each generation. Strings are super common in ASP.NET Core applications. There's strings everywhere. Actually, I think the most allocated thing we see in ASP.NET Core applications are strings, and tons of duplicate strings as well in the applications.
And that's not, it's not surprising.
It's not wrong, it's just
because HTTP is a text-based protocol. And so everything
you're parsing input from the wire,
and then you're sending text back more often than not, HTML or JSON, and so you often allocate. And in .NET, it's a string. Of course, that's what you use, right? And that's the thing you all learned sort of first. So, but you have to be careful.
I've seen a ton of code reading the entire request into memory and logging it to a logger, which is fine.
That's quite common, it turns out.
Which is fine.
Anyone here log their entire requests and responses to logging, to the logging system? Sorry,
don't shame anyone.
And people want, because they want accountability, they have traceability, the auditability, all these things. I have to log every single request. It's like, okay, that's going to impact your scale. Like, you need to think really hard about how you're going to do that without affecting both the throughput, the performance, and the scalability
And
of
security.
your application. And security.
Yeah. You're supposed to dispose disposable objects except for HTTP client. That's kind of a common source of resource leaks. Async local is this magical type that flows implicit state across an async boundary. That can leak actually pretty badly. And I can show a demo of that later on. All right, I/O, number of open file handles and sockets on the machine, a thing to watch for. On non-Windows machines, you can look at the U-limit of the actual machine to see if you hit the limit or not. There are I/O threads in the CLR made for mostly socket I/O and file I/O. Looking at HTTP client, your database connections to make sure you're disposing them. File stream is kind of a dumpster fire of badness to do with async. I'll actually go over why that is as we get through examples. Buffering is kind of what I said with small writes and reads from the network. All right. Sync over async. Who remembers this
From last year.
From last year.
Anyone come to last year's talk or watched it online? OK.
All right. Does anyone do this in their applications? Yeah?
Do we want to deconstruct this so people understand? We have a synchronous entry point. There's no async there. It's just void returning. There's no task. And then instantly, we're going to execute a task. This one's obviously made up, task.delay. But task.delay is asynchronous. Right? It creates a timer, gets put on the queue, and it'll call you back 5 seconds-ish from now. And then you've immediately put a .wait on the end. So one thread is being blocked. And then when this fires at the end,
so how many threads get used for this?
How many threads are going to get used?
How many threads?
To finish this app.
To run this code. Anyone?
One.
One,
We're going to vote of one. We're going to vote of two.
I heard two.
Any other call? Any
Four?
other votes? Just one. At least two from Mr. Skeech.
OK.
So two or more from here. OK.
OK.
The answer obviously is it depends. But I would go with at least two as the most correct.
At least two is correct.
Yeah.
So why is it so bad? So sync over async is actually much worse than just pure synchronous code, because sync code just blocks one thread, the calling thread. Sync over async blocks the calling thread waiting on the async operation to finish, which will then end that call and resume that work. So you block two threads for every async operation. If those threads happen to be both thread pool threads, you end up having to queue more thread pool threads to complete the work in the first place.
Right.
So you can end up in a trap where you're blocking thread pool threads and then requiring more threads to actually complete those operations. So you can end up in a death spiral.
And then if work keeps coming in, because someone keeps hitting F5 with the browser,
It won't recover.
Right. Then it'll never recover, because you can't keep injecting threads. It's a finite resource. And the system wants to schedule more work, which requires more threads, but it can't complete the work it already has, which it needs to schedule more threads in order to complete. So you can see how that gets really bad really, really quickly.
The thread pool is basically an unbounded queue. So it will just keep queuing work forever.
Right.
And it just won't run. Right. So we add threads at a very slow rate to prevent from overscheduling. And that's kind of the issues with separation in the first place. Because you block more threads, and then we inject more at a very slow rate so you don't kill yourself with the work.
Yes. But that assumes that the work's going to back off.
Yeah.
It's all done on the assumption the work's going to back off. Who's ever tweaked the thread pool configuration size? Come on. Who's read a blog post or gone to Stack Overflow and they go, oh, max threads, I'll just change that. Has nothing to do with this, right? All max threads does is you don't start out with max threads. You start out with whatever min threads is.
Number of cores.
As soon as which is number of cores by default. And then if you ask for more work, it will just very quickly go, oh, you're not up to max yet, just give you a new thread. But once you hit max, it doesn't just stop. But it's very slow after that, right? So
but if you hit max after it stops.
It does?
Max stops.
Seriously? Like
max
actually stops?
Max is really high by default.
Really? Yeah, OK. I don't believe it.
Thousands of threads. Super high. That was a great screenshot. So it's two threads. It's at least two threads.
At least.
Tasks do this crazy trick where they basically try to resume, super segue. If you wait on a task, the thing that completes this task, it'll always try to only run on the same thread. Even if you said you wanted it to dispatch somewhere else, it'll ignore your code and say, I'll run it on this thread. So you end up not using 3 threads in some cases. So this is a thread pool thread. This is the main thread, and it's completing this work so you can resume the actual
This is the app we just saw. This was a really simple app. So
that app.
program main on the left, starting at the bottom, and then the timer queue for the task.delay on the bottom right. And this is where they're both waiting on each other.
Yeah.
Right.
Makes sense? Yep. All right, let's demo a simple sync over async demo. Let's see if we can run this. So I have this tool written in Go. I have no idea where it came from, called Bombardier.
Called Mine Bitcoin.
Can you guys see this? Is it too small? Let me.
Beautiful.
Is that good size? Can you guys see it in the back? Yeah?
It's an XE.
I didn't hear no, so it's fine. OK. And I have this wonderful app that some architect wrote. And
Your title is architect, isn't it?
what?
Yeah, OK.
Yeah. So your architect gave you this beautiful service, and the old version had a get values method that was synchronous. But to be modern, they had to add a get values async. So this got added, and it has a super slow network call. You can't. This is fake.
You get that? You had a synchronous method at the beginning.
Get values.
You're slowly moving to async, and there's a period where you have both.
So you're changing your code, so you have this get values async. So you've modernized, and you added a new method that's async.
Right.
And you changed and to maximize method reuse, you're calling the async one from the synchronous one doing dot result. Yeah?
Anyone done this? Surely. Yep. Admit it. I mean, I've done it. It's terrible. Don't do it. Hang on. Why is it terrible?
No judgment.
No judgment at all.
Nope.
OK.
So then Junior Devs comes along and calls the synchronous APIs because they have no idea that they're supposed to call the async ones, right? So they call getValues.toList just fine in this control action. You run this now. Super slow, right, to run. 5 seconds at least. Perfect. It's working. So now I'm going to hit this thing with some load. Localhost 5000 API values, and see what happens. So let me hit it with like 30 requests.
No, it's all right. He's doing one is HTTPS and one is HTTP.
I don't trust it.
It's all good. David doesn't trust HTTPS on stage.
Just right now. Just for now. And that should take a little bit.
It should take some time.
Super slow, right? It's 5 seconds per request.
5 seconds per request,
5 seconds per
125
request.
connections, trying to complete how many? 30 requests
30
each?
requests.
OK. Math. That much time. Okay,
Yeah.
good.
1 RPS. Oh my God, this thing is super slow. All right, so now let's figure out what went wrong. I can do 2 things. I'm going to attach the debugger and try to catch this in action. So let me hit F5 instead of Control F5 in debugger. And I'm going to try to cheat and set a breakpoint in the timer itself.
In the framework.
This may not be actually good, though. Could be a bad idea. Yeah, maybe a bad idea. Has anyone ever got a process dump on Windows? Ever gone through that process of getting a dump and like shipping it somewhere because it's like 10 gigs and you have to zip it up and put it somewhere else? Yeah, it's terrible, isn't it? Let's try, huh?
Compresses really well.
It does, it does. Maybe dispose? Maybe a bad place. Give it time, give it time, give it time. Pause. OK, so I can look at threads, debug, Windows, threads. Here we are. You see a bunch of threads blocked on wait. Does anyone ever use parallel stacks? Not too many hands. OK, you should use this thing. Super useful. So it gives you this beautiful visual view of all the threads in the system, and it merges things that are the same stack. So you can see I have 14 threads blocked in a task.wait here. And this is kind of one of those signs of knowing when you're in that case of doing sync over async, where you see a task.wait here at the bottom of the stack. Right. So symptom is the CPU isn't being used, memory is flat, you have a high number of threads, and they're all blocked on some resource, right? So if you see those things, you probably are encountering sync over async. and you have an issue that you should fix.
How do I fix it?
Write better code.
Oh, okay.
Yeah? And
What if the issue is in the framework?
File a bug.
Okay.
And go close it. No,
Has that ever happened? It's funny because I'm looking at this sample you did, which was we had code paths that were synchronous.
Yep.
And then we introduced async code paths, and then we made the old sync code paths call the new async code paths with a dot wait, because why would you want two code paths?
Just
make
code
them the
reuse.
same. And it reminds me that I believe there are lots of places in various parts of .NET that may or may not have done that.
I don't believe that.
No.
So the fix would be to have the synchronous one be actually synchronous and do this, right? This would be sane.
Right, but now I've got duplicate.
But that's code duplication. So what
Code
if you fix
duplication.
a bug here and that's in there too, right?
Right.
I want to show looking at a dump just in case no one has seen it before. So to get a dump of a running process, there are APIs that you can actually call to get a dump from a process, but I'll show you how to do it from Task Manager because it's kind of convenient sometimes.
Assuming you have access to the
You can also get it in Azure App Service. You can get a dump from there, a mini dump. So I can go to details, find the process called .NET XE, and then right-click, create dump. This thing right here. Click on that thing. It'll create a file in temp. You copy it over to you zip it up, copy it over. It's really big. It's like the entire address space of the process, so it's super big. So you want to zip it up and put it somewhere else. And you can open it up in a couple of tools that I'll show you today. So the first one is good old Visual Studio. You can just take a dump.
Say capture, it sounds a lot better.
I can just capture a dump.
Capture a dump.
And drag it into VS, and I get this view, the dump summary. Has anyone ever used this feature of VS? Yeah?
I love this view. It's great.
So I can do a few things.
Does this work in every SKU now? Wasn't there a time when this didn't work in the community SKU? It was for a while. I think someone said that, I thought, OK.
Oops.
You have to install the Windows Development Toolkit? OK. A developer kit? OK. That's good advice.
It always runs out of memory.
And it always runs out of memory. Great.
Whoa.
If your
too much
dump's too
feedback.
big.
Too much. OK, that's fine.
Use smaller machines with less memory. The dump files will be smaller.
Have a smaller process. So dumps are sensitive to the version of the CLR, the bitness of the process, so 64-bit, 32-bit. So if you want to actually look at a dump on a different machine that you took it on, you have to actually have the right version of the CLR and the right version of and the right bitness to look at it.
Which is something that we're working on. We'd like to make it not so
it's really hard.
fragile. It's different.
It's also OS specific, so you can't take a dump on Linux and copy it to Windows and look at it in VS. That doesn't work at all today.
Yet.
We have plans that I'll show you some tools we're working on to potentially make it better to look at these things offline. So I can debug with manage only. And I'm back in this debugger view. And I can't step because I'm debugging a heap, so I can't step anywhere because there's nowhere to go. There's no process running. I can still use threads. I can steal the threads. So if you're in a situation where your process is kind of dying, you can get a dump and put it in VS and look and see what's happening. Open the threads window, and here's a different dump. So it's 15 threads, all blockchain weight. So same views for different kinds of things, right? So offline versus live debugging. So this is a good tool to use.
How many people didn't know that you could use half of the debug tools in Visual Studio on static dump files from the process? Okay. Wow. Ooh. Wow. OK.
Oh, cool.
Good. Well, that was well worth it.
Oh, look at that.
For that.
And you can click on the stack and see variables if they're not super optimized away. You can see some of them.
Yeah. Now, obviously, that's a good point. Often you're taking these from production where you did a release build. Now, if you deploy your PDBs, then you get a little bit more.
Yep.
But some stuff just gets optimized out at runtime. The JIT's done stuff, and it can't figure out where it is anymore.
It's not in a stack anymore. It's gone into.
But it's better than nothing. It's a lot better than nothing.
Yeah.
And we'll learn a little bit later that in conjunction with dumps, you can also use tracing, which can sometimes help you fill in those gaps that you don't otherwise get. So.
All right. So.
Deploy files on the machine where you're running this in the same folder location. That's fine.
Yeah, we'll find them.
Yeah.
Yeah.
Location, you can go to the module view and then just.
Yep, and load the symbols.
Load symbols.
But symbols will still only get you so far, because if the JIT's optimized stuff away, it's gone.
Yeah.
So
one more thing I want to show is looking at the heap itself. I guess I can show it in a different one, but the things you can do here, you can debug the actual core dump, and you can actually look at memory. So if you have a leak, for example, you can debug manage memory and look around and see what's in memory. The objects, all the roots. So you can, ooh, this is nice. You can sort by count. If you have a leak, sort by size. Oh my gosh, that's a lot of types. And you can see what things are being held onto. So I can look at, for example, service descriptor. It's funny. Find a specific instance and look at the roots here, down here.
Do people know why that's useful?
If you want to figure out why something is being held onto,
Right.
it's called being rooted. So
We're going to talk about leaks next, right?
yeah,
Maybe this will be better.
Yeah, this is in the actual
Okay,
thing. Okay, so let's fix the bug first.
cool.
Let's do what we should do and make this. Where's my controller? Make this thing asynchronous. So I'll make it async, adding a task. This type looks gnarly, isn't it? Task of actual result of enumerable string. Should fix that.
Yeah.
I have to make this async. And I have to await this. Does this work?
There we go.
Yeah, okay. All right. Should we take bets? Is this going to be faster?
Who thinks it'll be faster now that we've removed the contention?
5 seconds. So
5 seconds. Some people think it'll be faster. Everyone else is like, I'm not putting my hand up. I don't know what's going to happen. Wise.
No takers.
Very wise. So same load as before.
Still super slow.
It's the same speed. There you go.
You know why? It's because scale isn't performant. So you don't get more throughput. It's still taking 5 seconds per request, right? You haven't fixed anything. You made it so that there aren't 5 threads blocked, but you still don't have more throughput, right?
So in theory, could it handle more load? Is that
In theory.
what it's about? Like
Theory,
more
yeah.
concurrent people?
I think the first time I got 0 RPS, now I got 6. So yes.
Okay, very good.
Yes.
So okay.
So it's better in
Good.
that case. It also doesn't use any threads. So if I were to debug this code again, running it live,
Ooh, that's a good point.
I shouldn't see any threads if I can debug in time.
So we had 14 threads that were blocked before?
Yep. If I
Right.
pause debugger, is it still? Oh, hold on.
Wasn't running?
Yeah, it's too fast. Let me hit F5. I'll go to this thing. Hit it again. And pause like now. Threads.
Well, oh, wow.
Boom. Super efficient.
Okay.
So when you go to async, you don't use threads. But the biggest downside is that you can't actually see where your code's running, right? So imagine you had an async hang where you had an outbound request to your backend service that didn't respond for some reason, for some lag, right? You can't look at it in the debugger and see it because there's only memory.
So you're saying,
There's no code running, right?
before we basically had as many requests as we had threads running because they're all blocked. Now we have lots of requests running. We just can't see
threads.
them in the same tools because they're not using any threads. There will be memory for
There's
them,
memory,
I'm guessing.
yeah.
So if we looked at your heap snapshot, you could maybe find types
Good luck.
that represented the threads.
It's insanely hard. to
Sorry,
look
the requests. Okay.
Yes.
That sounds like a problem we should
So you
solve.
got more scale, but you can't see the actual things running anymore.
Great.
So you got trade-offs, right? It's all
If I can't see it, does the problem
all
exist?
software engineering. Nope.
We will fix that, surely.
Yeah, that's being worked on. So we want to actually support a view called parallel tasks, where we have the same Windows parallel tasks, but we show the actual async state machines in kind of a chain
Right.
of calls. But it's really hard to do properly. Who has this code in their application?
Some derivative anyway. Yep, John's got it. Yep, my hands.
It's fine. It's
Yeah.
not. This is okay. It's okay. It's
pretty standard,
This code
right?
is fine. What's wrong with it? Does anyone know what's wrong with this code? The lock. The lock makes it work, though, right?
That's right. I mean, you can't not lock, right? This one has to be thread safe. It's going to be used in a
So
web
it's
application.
used in the modern service because this is modern.
It's modern?
Actually, yeah.
Okay.
It's being used in the web service, so it has to be concurrency safe. And locking is actually completely fine.
Right. You want to lock.
The only issue is if this becomes a super hot lock, if you're doing actually hot CPU work in that in this creation phase, it could be a bad thing. You have high contention, right?
Add another heap before lock.
You could do that, and it would break on ARM, so you couldn't run on Raspberry Pi, which is fine. But
the double-check locks,
don't work
differently on x86 than they do on ARM because ARM instructions can reorder.
But you're fine. You don't need to run on ARM, so you can.
It's fine. .NET does the right thing if you use the right things.
You can do that.
Maybe.
Concurrent dictionary.
There we go.
That is
Concurrent
one
dictionary.
That's right. So apps are very concurrent on the web. Concurrent collections are actually a better thing to use in this case, but we'll see why it doesn't help in some cases all the time, right? It's really hard to see contention in basic profilers. Some of them show it, like .trace's timeline view, and there's a plugin for VS called the Concurrency Visualizer. I can show you right here. I'm not sure if there's one for VS 2019 yet, but there's one for 2017 and 2015. And it gives you a really pretty view of looking at all the threads. I'm not sure if there's a picture here.
Is there a screenshot?
There used to be one somewhere.
Utilization view on the left. Threads view and you on the left. Yeah,
This
that'll
thing?
do. Yep.
Oh, threads view.
Yep.
So it gives you this kind of view, which shows you all the threads in parallel and tries to show you where locks are happening on the same threads. So you could use this tool to see if you had contention or not. Some profiles will show you that there's contention on like the lock call. So, but it's really hard to look at it in a profile and see that you have a hot lock, right?
.NET Framework, I think there's even a perf counter for contention locks, but there isn't.
Number of contentions per second.
Number of contentions per second, but .NET Core doesn't have perf counters.
Yet.
Are uncontended locks still deemed cheap?
Cheap-ish. Vance would say, who's the .NET perf architect, would say that locks are like not cheap, but they're pretty cheap if they're not contended for the most part.
If they're not contended.
For normal apps. It's only for super high perf stuff that where it would be expensive.
John asked the question, are uncontended locks still considered cheap? And the reality is, generally speaking, yes, unless you have an incredibly hot path that is sensitive, and then it's worth the effort to try and write lock-free code, which is really difficult.
You shouldn't write lock-free code. It's way too hard.
Really difficult to do.
When you use concurrent collections, you should know which operations lock and which ones don't lock. So for example, concurrent dictionary.triad will lock on that key. If you get the count, it locks the entire dictionary. If you get, it's lock-free. So knowing what to call in what situation is actually super important.
Right.
If you don't, then it may not be any better than what you had before with a global lock of the entire dictionary. Sorry.
And the lack of observability, just like you said, makes it harder. So knowing ahead helps, but it's difficult to know.
And then if you call certain BCL APIs, they may take locks on your behalf. So like string.intern, for example, GDI, there's been a lock in GDI since the beginning of time.
We've always recommended system.drawing not be used on servers. Like if you look at the official documentation, it says do not use system.drawing in your system.web application. And it's really bad because the locks aren't just in the CLR. The locks are like
in the library
wide. Because GDI is a native component, and so it has its own logic. So yeah, you've got to be really careful sometimes.
All right, let's try to show this. So this demo, just warn you right now, it's really hard to show it. So I'm going to show just the code and kind of how the code would change.
It's a bit of a leap of faith here because some of these things can be hard to demonstrate on a laptop.
This was a hard one. Do not open. So there's a picture of me with a region on Twitter. This is the region, OK? It's trying to just be a fake CPU burning algorithm.
Trying to do work.
Trying to do work, right?
OK.
So here's the code. There's a lock. Try to get value by ID, right? So let's run a super simple perf test on the get by ID controller. Get value by ID calls that service, calls get by ID, does a hot thing, and then catches it and then returns that value, right? Super simple. Let's see, values, 12. All right. Run that, runs for 10 seconds, give you some numbers. You guys can't see that, right? I need to shrink this thing. What?
Oh.
Hold on, 5?
It's shut down.
Maybe I made it too crazy.
Did you kill it?
Hold on.
That's awesome.
Let's try this. Let's get a good number first, so I can show something. So that runs, it should get like 20,000, 30,000 RPS, my machine. Yep, perfect. That's with the lock, right? Super fast lock, not held very long. Let's try concurrent dictionary, see if it's better. I'm gonna call cache.getOurAdd. This is the old code. This is new code. Should return this. So, any guesses? Is this faster? No?
No. No one's willing to say
No
yes now
yeses?
after the first one.
Why isn't it faster?
You never have, you're only calling grid.newgrid once because you're always fetching the same ID.
Okay. I'll take it for now.
So much drama.
Yeah.
About the same.
It's about the same thing. That's noise. It's the same because concurrent dictionary actually, so two reasons. This is a bad perf test because it's the same key the whole time. So it's all people hitting the same thing. So that thing gets hit once ever for this test, and it's
Right.
cached for the whole time, right? The second thing is concurrent dictionary actually locks on the key. So for the same key, it's the same as having the same like one giant lock, right? So it's only one key. You should see better results if you hit it with different keys at the same time, unless those keys hash to the same bucket.
Yeah.
But numbers have a hash code that's themselves, so it should be distributed properly.
Right.
What's the other issue with this code? Well, no one called it yet. What's the other problem with this code? Anyone see it?
So we fixed the lock contention.
The lock contention.
Kind of,
we
mostly.
think.
What else is wrong with this code?
You've watched the talk already. Did you see my slides? This is an unbounded cache with like taking stuff from user input.
That's even worse.
Security hole and a memory leak at the same time. So how do we fix that one?
How do we fix the unbounded cache problem?
Can you tell me how to fix it? How do you fix that? How do you fix that one?
You hire a consultant.
Hire an architect.
iMemory cache? I heard iMemory cache.
Would that help though? It just
It's got a limit on it.
does have something on it.
And it has some cache semantics, like it will maybe clear itself, or items, maybe, sometimes, does it?
So memory cache has
Calls itself a
support.
cache.
It has support from, not this one, I think it's memory cache. Memory cache.
The concrete type.
Yeah, it has support for, I believe, size limited? Is it in a different version?
Percentage, compact, and
That's not here.
the item. Don't you have to add items to it? The options. Oh, it's in the options. There you go.
Yeah,
Size limit.
this thing, size limit. It's not super useful, to be honest. It only works well if you're saving things that can be counted, like bytes or strings or something of that nature. Not for general objects, because it's hard to know what size of things you're actually putting to a dictionary, right?
Right.
So it would work here for strings. You could also limit the number of entries in the cache itself, but that ends up being super hard because now you have to actually like figure out how to basically do this, right? If cache.count greater than 10, then like remove something from there, right, and keep doing that. But then you have to actually have that be synchronized with the actual
Why isn't there a type
adding and
that
removing.
does all this for me?
There's a type in Java that actually does
Java? That doesn't help me.
Yeah, but nothing in .NET.
Okay.
So you could do a count again, which would take a lock on all the buckets in the concurrent dictionary. But then you may be actually highly contented again.
Is there a good NuGet package? Seriously, is there a good open source .NET cache library that anyone uses? Anyone built their own?
You said
homegrown one? I know they exist. I've heard John's built one.
Does it have locks though?
I think so. It's in there.
Yeah, it's fine. It's fine.
Okay.
Locks are fine.
It's actually a really hard problem.
Yeah.
To write well.
Yeah, not easy to solve.
System Web had an in-memory cache. that was completely private and relied on private things to work well that don't exist in .NET Core yet. We're looking at adding, so like the problem that David just said, which is what you really want to be able to say is just add stuff to it, and if it gets too big, flush stuff out, right? That's what you want, right? But if you add a random customer object, how big is it? I don't know. Like, how do you calculate the size? Look at all the tools we had to show you to use to even like walk the heap after you take a dump and to calculate the size. It's not straightforward today in .NET. The runtime itself knows better.
It knows very well, actually.
And it does really well.
But it won't tell us anything.
It doesn't tell us yet. But
Yet.
we're talking
Yet.
to the runtime team to try and get them to add an API that they're comfortable with that would let you do this type of thing.
So you could use the iMemory cache to add entries and then have a policy to evict them at some point. It doesn't help the size issue, but it helps the fact that like the cache would grow forever because it would.
Right.
I think we start to kick things out if it goes over a certain size
Right.
by default.
It gets kind of wonky though, right? Like, because if you're in a
It does get
multi-core
wonky.
system with multiple heaps, you could have an object graph where objects are spread all over different cores.
No, that's not a thing.
Okay.
No.
Sure, really?
That's crazy. No.
That could happen. Yeah.
Who has this code in their application? Yeah? No one? I don't believe you. Yeah. It's fine. No judgment. No judgment. It just allocates a giant string first, and then it turns into an object.
It's so easy though.
Yeah. It is very
So
easy.
easy.
I blame James for that.
Okay.
Because this API takes a string, not a stream, so like it got easy, right?
Yeah.
Okay, so this is all fine. Allocated memory is very cheap. Like doing a new object is actually super cheap. If you have too many things that last a long time, it can lead to GC pauses. If you allocate more than 85 kilobytes in a single allocation, it'll put it on the large object heap, which is kind of like the place where objects go to die. And it can lead to leaks, right? So you want to avoid that as best you can. And the issue with this code is that depending on the size of the request byte that you expect, you could end up creating a string on the large object heap per request, right? It's a really bad thing you can do. So let me demo some awesome code that does the wrong thing.
Just
right thing.
sideway comment here. Do things like MVC just do the right thing? Like if I like model binding
Yes.
and value providers, they do the right thing here?
That's correct.
Okay.
They do.
So rather than doing JSON deserializing myself from the request, I should use the framework.
What if you want control, though? What if you want,
If you want control, you have to accept that with control comes something.
Well,
Comes responsibility. That's not quite the quote. That's why, but you know, still, it works. It works.
all right, so we're going to see some interesting
Nothing's
things
free.
here.
Put it that way. How's that?
So to make this one work, I have this API. I'm doing a post. This is a great tool, by the way. It's a post, and I want to upload this file.
File name's kind of long.
Is it?
Bombardier-Windows-WinAMD64.
It's a weird name, Bombardier.
Optimize for Intel dash.
This file is Pokemon. I might get sued for this, not sure. Upload the Pokemon. I think that's good. I want to send one request first to make sure it's doing the right thing. Let me debug this call, make sure we're all fine before I hammer it with like 1,000 requests. 5 seconds, sure. All right.
Okay.
All right, there we go. There's Pokemon.
Nice.
All right, that works. All right, so has anyone ever used perf view? I'm sorry. Really? On purpose? Okay, so perf view is a tool that's written by the CLI architect. It's not very friendly to use, but it's super powerful. It can pretty much see everything going on the OS and in the .NET framework, but it's insanely hard to use. But there's tons of videos you can watch to figure out how to use it. And I have not watched any of them, to be honest. I just figured it out by asking him on email in a rage, like, how do I use this thing? So I'm going to run this. Here's the thing to upload the file, more than one request. I'm going to run the app. And I'm going to look at perf view, tell it to collect. So you aren't supposed to press this tab because like, under here is super advanced. GC collect and GC only. See what it does. And then I'm going to run the perf test. and then go back here and say start.
Something tells me this UI wouldn't pass all the accessibility tests that Microsoft usually puts their software through.
Yeah, it's pretty
All the high DPI tests.
pretty good. All right, 1,000 RPS, it's done. I'm gonna stop collecting now, and Perfy will be working. It's working super hard, it's ready. All right, let's see what it did. Memory, GC stats, and it collects the entire machine, not just that one process. So you have to find your process in this HTML page. And it allocated 2 gigabytes.
Whoa.
It's not bad. A second of GC pauses, large object heap allocations. Where is it? Alloc large, off the wazoo. Yeah, so this, but it had decent RPS, so maybe I'm fine. Let's try doing it differently. Let's try using MVC's built-in from body.
OK.
From body. Get rid of this, and this should be, what's it? It's even easier to type. Look at that. Less code I have to write. All right, let's run it again.
Seems less microservice-y, though.
Does it?
I'm relying on a framework to do it all for me.
Yeah, it's not
I don't know
powerful.
what's going on.
Let's collect again. I'm gonna run this thing first, and then rush to collect, rush to say start. And it preserved my options, so it's a good tool. Oof. I lost it. Did it finish?
OK.
It's done. It's much slower though. Ugh, damn it. But it's easier. It's working, it's ready. OK. Same thing, GC stats. Sync over async. OK, look at that. Allocated
Just
1
under
gig.
2 gig. Just under 2 gig. Calling it a gig is generous.
The other one.
I mean, I could have let that slide, but I couldn't have had a straight face in front of all these people again.
Pause time is like minimal.
OK, that's good. No pauses.
No pause time.
It was what, 1.3 seconds or something before
Yep.
of total pause time?
Yep.
Yeah.
Allocations are all small, nothing on the large object heap, but it's slower.
Yeah.
So here's an example of a trade-off you can make where the thing that is faster is actually bad for memory. So pick your poison.
Right.
Better RPS, worse memory.
Less latency.
At some point, it'll fall over and like, right? But it's pretty good, right?
Yeah.
Okay.
You can't have everything, unfortunately, all the time.
You can't.
Nope.
All right. Fix-ish. OK. Who here has this code in their application? So stare at this code. This code is trying to take a task that doesn't have an intrinsic cancellation behavior and time out the operation afterwards. So you take that task, you take a second task that has some timeout delay, and then you race both of them, so when any. So if the delay task finishes first, throw an exception. Otherwise, return the actual task.
Anyone done this? This is really common.
Makes sense, right?
Super common, right? It's almost correct.
This code is almost correct. But
Almost correct.
super broken. So timers in .NET are, there's a thing called a timer queue, and timers are a linked list. So whenever you call a new timer, it asks that list of timers. It's optimized for adding and removing. When you actually run a timer callback, it's on the thread pool. That's why if you have starvation, timers won't run on time. So you can actually get things out of sync by having starvation in your process. Each timer queue has a giant lock. And on full framework, it's actually one queue for the whole process, so it's really bad. On core, it's much better. When you dispose timers, it gets removed from the queue. It's kind of my pretty slide play.
So this is like .NET Core. I had two.
.NET Core has one per CPU, one per core.
So imagine I have 2 cores.
.NET Framework has
And
one.
these are my timers,
Yeah.
and that's the queue. OK.
And when you call remove, it goes away. If
Okay.
it fires, it goes away.
Okay.
By default, it's in the queue.
OK.
All right, so let me show. I have a dump that I'll show, so I won't actually debug the actual thing. But the app that I ran this app beforehand. Call some external service and then timeout after 30 seconds, all right, to make sure it never runs past that.
Which under the covers is doing exactly what?
Yes.
that did before. Yeah, timers are a lot more popular now than they were like prior to .NET 4, really. Once tasks came around, and then with async await, and it became very easy to fire off async work, but you wanted that work to time out, you either did it manually, or there's now intrinsics. You use Poly, or you use a library, an API in the framework, and it'll be doing this for you under the covers. So timers are created everywhere now. It's very, very normal.
So I'm going to try putting it into Visual Studio, and I'm going to try debugging manage memory. Hope it doesn't crash or fall over.
That's a lot of objects. That's a lot. Oh, 5 million, I think I
If
got
this
to.
thing crashes, please don't crash.
You've got RAM, right? No? All the RAM?
Yep.
There we go.
Ooh.
There we go. Super reliable.
OK, look at that thing. Timer, QTimer. Those are the individual timer entries in the linked list. So the reason this is happening is because if the operation finishes fast enough that the timeout kind of doesn't matter anymore, it'll still be in the queue because no one said to dispose of the timer, so it'll hang around for that duration. If I keep doing that, it'll just pile up forever.
Go forever.
Go forever.
OK. This
So
is a timer leak.
timer leak.
Right? OK.
So every time the timer ticks, it'll loop over all timers and fire them in order.
OK.
So it's very inefficient.
So this gets worse and worse.
it gets worse and worse.
OK.
So the fix is to do this. Create a token, pass it into the actual time, into the delay, and then if the thing that finished wasn't the delay task, cancel the timer. And this will actually stop, this would get it out of the actual timer queue and have it not leak anymore.
Wouldn't the better fix be for this to be in the framework?
I found the bug. After I found it, I agree. I super agree. So yes, I agree. It's so common that it should be in the framework itself.
Did we find this because a customer found it?
I found it when I was making this talk. So we found it on a test I think we wrote for Kestrel.
OK.
And the test was hanging.
Oh, this is the flaky test?
We saw a million timers.
That's right.
And it was like, yeah.
We'd have tests that would randomly fail.
Yep. OK, more fun. .NET async traps. What is wrong here? This looks fine, right? It's asynchronous. It's calling write async. It looks all good. What's the issue? I'll tell you what the issue is. So this type actually buffers the data it writes. So when I call write async, it stores it in the buffer. It's only if the buffer is exceeded that actually goes to the stream. So what ends up happening here is it buffers hello world because it's a very small payload, and then dispose will write it synchronously to the actual stream, which is really bad, right? So you think you're doing async I/O, turns out you're not. The fix is it's called flush. Crazy, right? Yeah.
So hang on. The problem was it implicitly flushes the stream
on dispose
after I've written, and it does it on a synchronous code path, which is dispose. Isn't dispose async coming?
Yeah, .NET Core 3.0.
.NET Core 3? OK.
So this is the case for every single type of stream in .NET that buffers. So gzip stream, file stream.
SSL stream?
Yeah.
Wow.
Anything that's, we found it because we turned sync I/O off in ASP.NET Core 3.0, and guess what happened? Everything failed.
That's a good point. In ASP.NET Core 3.0, to help you find these type of things, I tried to get it done in 2.0. I pushed, and then too much stuff broke. So in ASP.NET Core 3, if anything goes synchronous on the writing path, like sync over async, it will throw. The request will fail. And it will say, nope, you tried to do a sync operation in the async context. That has led to us finding a lot of issues in the framework, which is good, and people's libraries and all that type of stuff as well. So
what else?
Sometimes you have to be really strict in order to find the issues that you want to weed out.
There's a pattern here where you call get or add, and the actual thing you want to actually do in the callback is asynchronous. I've seen people do .result there. It doesn't help. It's actually the same issue as sync over async. What you can do instead is store a concurrent dictionary of something to task of blah. Then the issue is that you may end up running this callback multiple times because it can run more than once per key, right? If you want to stop that, then you just do a lazy of lazy of task of t.
An async lazy, you mean?
I made a type to make it less generic.
OK.
And more lambdas to make your brain explode.
Usually, if the lazy fails, then you'll getting an exception rather than it.
Yes,
that's pretty bad.
There's no error handling in that one.
Someone should fix that bug. Send me a pull request. It's pretty common if you want to connect to some backend service at startup or in lazily. So you have a factory that connects to a thing, and it gives you a connection that does pub sub, like Redis, for example. People do this in the constructor.
Oh, who needs to
Right.
do asynchronous work in their constructor?
Yeah, because you want to
sometimes?
get the connection super early, and there's no sync
Right.
to get it. Oops. There's no good fix here, to be honest. You have to like, just change your life.
Just don't do it in the constructor.
Yeah.
I mean, right? I'm sorry. There's no other fix for that currently. You have to re-architect it to not do that.
Okay.
Do you want to show your doc before the end?
Yeah.
We are going to work on a lot of this stuff. So the future enhancements, so David's working with a bunch of folks at Microsoft to try and build a set of tools, whether command line tools, Visual Studio features, and analyzers to help you find a lot of these things while you're coding and then analyze them after the fact as well. Obviously, a lot of the stuff here is difficult. So this is a bunch of guidance that Fowler's been working on his repo.
Yeah, for
David
now.
Fowler, ASP.NET Diagnostic Scenarios.
I mean, it has a ton of followers. That's crazy.
Yeah, so check that out for what you saw today. I think it's examples of everything you saw today, plus a whole bunch of other stuff as
Yeah.
well, right? Cool. And with that, we're done.
Yep.
We're out of time. So thank you very much again for coming. Please check out that stuff, and we'll see you next time.